Okay, next we are going to discuss question number 6. Basically, that is the CRO screen. So, if you haven't read it or didn't try it, please pause and go and read the question. So, basically, a source of radio wave sends a pulse towards a reflector, and the reflected pulse comes back, and the original pulse and the detected pulse after reflection is displayed in the CRO like this. The time-based setting is 0.2 microseconds per centimeters. Use figure 2.1 to determine the distance between the source and the reflector. So if you want to find the distance, now first they are saying, okay, if you want to find the distance, now all these waves travel with constant speed, so distance is equal to the speed times the time. So time we can get it from the CRO screen. So if you look for the first pulse, the center of it, and the reflected pulse detected, it is here. So 1 2 3 4. So 4 boxes, 4 centimeters. Each centimeter means 1.2 microseconds. So the time is equal to 0.20 times 4. This is 0.8 microseconds, right? 0.20 microseconds per centimeter times 4 centimeters gives you 0.80 microseconds. So this is the time. Then how will you find the speed? Well, this is a radio wave, and the source of radio wave, the pulse returns and reflector and some point, the emitter. So it's a radio wave, so we can say take the speed is equal to 3 times 10 to the power 8 meters second minus 1. Hence the distance will be 3 times 10 to the power 8 times 0.8 naught. It is micro. Micro is 10 to the power minus 6. That should give you a distance of 240 meters. D is equal to 240 meters. So this is the time for it to go from the source, get reflected and come back. That means if the source is here and the reflector is here, and this distance, so twice this distance is the one we calculated, 240. So the distance to the source, distance from the source to the reflector will be 120 meters, right? 120 meters. Now the next part, determine the time-based setting required to produce the same separation of pulses on the CRO when sound waves are used instead of radio waves. So now instead of radio waves, if you're going to use sound waves, they're asking what would be the time-based setting, well, like what is the scale you would use, and that scale should mean that the time taken for the sound wave to travel should also occupy 4 centimeters. Like if they are saying that determine the time required to produce the same separation of pulses, so if the pulses should be separated in the CRO by the same amount, that means 4 centimeters, that means that the 4 centimeters should denote the time taken by the sound wave, right? So if we know what is the time taken by the sound wave, then the time is representing 4 centimeters, then we can find what is represented by 1 centimeter. So that will be the time base setting, the scale, right? So for that we need to find the time taken by the sound. So basically this question is asking what is the time taken by a sound wave to travel the same distance. That is the question. Instead of asking it directly, they are kind of making you confused, like the pulses and separations. But basically, like in the first question is a radio wave, and now they are asking what would be the time if a sound wave is used. So that is the question. So the speed of sound is given as 300 meters per second. Now we know the distance that the sound should travel. So between the two pulses, the distance traveled is 240 meters, 120 this way, 120 that way, so 240 meters. So the distance is there, the speed is there, so the time taken by the sound to travel would be the distance divided by the speed, 240 meters divided by 300 meters per second. So that is about 24 divided by 3 is 8.8 seconds. So 4 centimeters should represent 0.8 seconds, which means that 1 centimeter represents 0.8 by 4 seconds, which is 0.2 seconds. So every centimeter represents 0.2 seconds. So the time base setting is 0.2 seconds per centimeter. For the radio wave, it is 0.2 microseconds per centimeter. Here it is 0.2 seconds per centimeter. Now, so that's the second method discussed here, the kind of a very clear method. There's a kind of shortcut argument you can use, that the speed of sound is 300 compared to the speed of radio wave, which is 3 into 10 to the power 8, which means that speed of sound is about 10 to the power 6 times lower than the radio wave, right? That means the time denoted by the base is about 10 to the power 6 times greater. When the speed reduces, where speed is equal to distance over time, so speed and time are inversely proportional. So when the speed becomes 1 over 10 to the power 6 times, the time becomes 10 to the power 6 times. So that is, for the radio wave, it is 0.2 times 10 to the power minus 6 seconds, microseconds. Here it becomes 10 to the power 6 times, so it becomes 0.2 seconds. But this method would have been quite difficult if they have given the speed of sound as 340. But even if they have given like that, this method would still work, the usual method. Okay.